Welcome to SPRingBoard. I'm your host, Michael Hannaman. Today, we're diving into a rapidly emerging frontier in climate innovation, marine carbon dioxide removal, or mCDR. As we confront the growing urgency of the climate crisis, it has become clear that the current pace of emissions reductions is inadequate to limit global warming to within 1.5 degrees Celsius, the target set by the 2015 Paris Agreement. In its most recent synthesis report, the Intergovernmental Panel on Climate Change concluded that globally, currently implemented policies have us instead on a path to between 2.2 and 2.5 degrees Celsius of warming by 2100. Absent immediate and deep reductions in global emissions, achievement of 1.5 degrees will require us to remove carbon dioxide that is already in the atmosphere. And that's where mCDR comes in, a rapidly evolving field that harnesses the ocean's natural processes to capture and store carbon. But how do mCDR technologies actually work? Can they scale fast enough to make a dent in global emissions? And what are the legal and social challenges involved in deploying them responsibly? To explore these questions, I'm joined by two very special guests. Garrett Boudinot is the founder and CEO of Vycarb, a startup pioneering a water-based carbon dioxide removal and storage system which is permanent and measurable. Meg Holden, a principal here at SPR, also joins us for this episode. Meg has extensive experience advising renewable energy and climate technology companies, including Vycarb, on federal, state, and local permitting and environmental review requirements. Together, we'll explore the science, economics, legal frameworks, and community dynamics shaping the mCDR field. Whether you're a policy expert, climate tech founder, environmental attorney, or just carbon curious, this conversation is for you. Garrett and Meg, welcome to SPRingBoard.
Michael, thanks for having me.
Thanks. Looking forward to the conversation.
So, Garrett, I wonder if you can start by telling us a bit about what marine carbon dioxide removal is and why we need it.
Yeah, certainly over the past 10 years, the kind of global need for decarbonization and particularly for removing the carbon that we've already emitted into the atmosphere has just become more of a pressing need. I think things like the IPCC reports that have highlighted the importance of pulling carbon dioxide out of the atmosphere to meet livable climate target, and then legislation and policies like that's what's been launched by the UN for global decarbonization targets has made this focus on carbon dioxide in the atmosphere and cleaning up, again, what we've already emitted, just more front of mind for folks. And there are traditional carbon removal approaches or offsetting approaches, things like growing trees that folks are typically well aware of. But I think folks are also looking at other ways that natural systems are already absorbing CO2 that we can accelerate, that we can leverage for meeting some of those climate targets. And the ocean is really the largest sink of carbon on the surface of the planet. It's already removing and storing lots of carbon dioxide from the atmosphere. And so that marine carbon dioxide removal as a sector of technology has really exploded in particularly the past maybe 5 years as folks are thinking about different ways we can leverage and accelerate that ocean carbon pool. I was in a former life a proper just climate scientist studying how carbon is cycled in the ocean system. And so as I was thinking about how we can not just study the problem, but develop solutions, something like marine carbon dioxide removal was a clear way to leverage some of those fundamental science skills towards having a positive impact. And for me, it was just really well aligned with, again, that global market interest in these kind of solutions.
And so when we think about carbon dioxide removal or marine carbon dioxide removal, can you explain what the differences are between the terms carbon capture, carbon sequestration, carbon storage, and how those fit into carbon removal?
Totally. And I think they mean different things to different people. So I'm glad we're starting with some definitions. Carbon capture and carbon dioxide removal are typically differentiated by the source of CO2. So carbon capture is typically point source. So that's taking CO2 from the point of emissions. So you think the tailpipe of a car or the smokestack on a coal furnace. If you can capture the CO2 before it even gets to the atmosphere, that's proper carbon capture. And then on the other hand, again, we've already emitted lots of CO2 on the order of 1.5 trillion tons of CO2 since the Industrial Revolution. That stuff has already mixed with the atmosphere, already mixed with the global climate system. And anything that pulls CO2 out of the atmosphere that's already been mixed, we would call that carbon dioxide removal. And then we've now got CO2 that we've either captured or removed. What do you do with it? And so then there's typically either utilization, so taking that CO2 and utilizing it for anything from, I've seen drinking alcohol to diamonds to sustainable aviation fuels to cement, or there's storage, which is injecting underground into geologic formations, and we would call that sequestration. That's a bucket within storage. And there's lots of other kind of storage solutions that are out there. So typically you would refer to CCUS, carbon capture, utilization, and storage. Or for a lot of folks, when they say CDR, carbon dioxide removal, they really mean carbon dioxide removal and storage.
That's helpful. Thank you for that context. So when we're evaluating the effectiveness and the viability of mCDR, marine carbon dioxide removal, or really maybe of any carbon dioxide removal technology, what are the key questions that we should be asking?
Yeah, I mean, in the industry, as folks are, trying to buy credits for carbon dioxide removal, there are a few key boxes that need to be checked. One is additionality. And I think this plays out particularly in traditional offsetting markets where folks were paying for forestry projects and saying, okay, we're going to count that as a carbon dioxide removal offset. Well, how do you prove that that forest that you're preserving to continue to remove carbon wasn't going to already be preserved? Or how do you prove that it was going to be cut down? And so that additionality question, is this an additional form of carbon removal, or was this already going to happen? That's kind of the initial checkpoint. And then after that, there are two real, I think, emerging focuses. One is on measurement and verification. So CO2 is an invisible gas. How do we actually know that it is being removed and stored into some often other invisible form? And so there's a kind of industry jargon, MRV, measurement, reporting, and verification, or monitoring, reporting, and verification. How do you actually monitor, measure that carbon, verify that it was indeed locked away from the atmosphere, and report exactly how much of that was locked away from the atmosphere? That's a big one, particularly in the oceans where, since we're talking about mCDR, where carbon is constantly transported and moved and it's a massive carbon sink. How do we trace where the carbon started and where it ended up is a real need. And then finally, permanence. So again, on the storage side, if you're taking that CO2 and locking it away, how do you know that it is locked away and for how long? So there are some forms of carbon dioxide removal and storage that might lock CO2 away for 100 years. And you're very confident that it's locked away for 100 years. But then after that, there's a high likelihood that it's going to go back up to the atmosphere. We would call that a less permanent form of carbon storage than some forms of carbon storage in the ocean or geologic sequestration, where we're confident that it's really been locked away for thousands, hundreds of thousands, even millions of years. And so that additionality, the verification, and the permanence, I think are the three biggest needs in the market for these mCDR and CDR generally.
Can I ask a question, Garrett? Could you tell us a little bit about some of the main approaches to removing carbon dioxide from the oceans?
Yes. So there's and I hesitate because this is a Pandora's box. I'll try and keep it focused. So maybe we can first split them off into biotic and abiotic. And so biologic, as the biotic alludes to, that's kind of recognizing that there's a lot of photosynthesis that takes place in the ocean. Photosynthesis takes CO2 and converts it to some form of biomass. And so whether it's, growing seaweed or kelp or restoring mangroves, these are all forms of what we call biotic mCDR, where that CO2 that was in the atmosphere ends up in some biologic, really organic molecule. I think this pertains to that discussion of permanence, because a lot of that organic matter is considered less permanent, because what happens once organic matter is produced, it at some point becomes respired and it goes back to CO2. And that's kind of the carbon cycling that happens in the biosphere. But there are plenty of mCDR approaches that leverage photosynthesis, and we would call biotic. And going back to the terminology of some of these, often that would be called blue carbon. So in the mCDR, in the ocean carbon solution space, there's a lot of talk about blue carbon. Traditionally, most people when they say blue carbon, they're referring to those biotic pathways. That is in contrast to the abiotic. And I might go a little bit down the science road because that's where my background is and where this really leads us, where the ocean naturally actually stores about 1 billion tons of carbon dioxide from the atmosphere per year through this abiotic pathway, not going through photosynthesis, but instead through inorganic chemical reactions that take CO2 and convert it to other non-organic carbon molecules. So, and I apologize, but we're going to talk a bit about some chemistry. All waters and ocean waters have 3 different forms of inorganic carbon molecules. CO2, that gas, HCO3, which we call bicarbonate, and CO3, which we call carbonate. And those are dissolved molecules. They're invisible, floating around in the ocean. They have different charges, and so the relative abundance of those carbon molecules is dependent on the other elements in the ocean that are dissolved that drive separate charges. And so carbon with these other elements like sodium and chloride, right, because we think of salt, magnesium and calcium, all of these different charges are essentially modifying or modulating carbon in the ocean. All of that is to say, actually, the majority of carbon on the surface of the planet in the ocean is bicarbonate, HCO3 minus, a molecule that probably most listeners have never heard of, but it's over 90% of carbon on the surface of the planet. And so, again, an abiotic pathway is naturally CO2 combining with ocean water, interacting with elements like magnesium and calcium and forming that bicarbonate, which, once produced, stays as a dissolved, non-greenhouse gas molecule for about 100,000 years. And so there are all these other forms of mCDR that aren't organic matter that are trying to leverage that inorganic or abiotic carbon storage pathway. Some are focused on that calcium and magnesium concentration. So adding a bunch of calcium and magnesium to the ocean, okay, well, now we've got a bunch more positive charge. That's going to essentially allow more of that CO2 to convert to bicarbonate. And frankly, going back a couple of decades ago, scientists started to think about this abiotic pathway for carbon removal and carbon storage. But within that, there are other folks that are thinking about how to remove some of the negative charged ions to increase more of that magnesium, calcium. So there's things like ocean alkalinity enhancement, again, adding things like calcium and magnesium, which we call alkalinity. There's electrochemical approaches to that. And then finally, there are groups looking at actually removing the CO2 from the ocean such that it can then absorb more CO2 from the atmosphere. All of those we would put under that abiotic framework. And I think pretty much anyone trying to use the ocean for climate solutions would fit somewhere in one of those categories.
So you mentioned seaweed cultivation would be biotic. Also, I would imagine biomass burial, biomass sinking, that would fall within the biotic bucket. And then the alkalinity enhancement, et cetera, would fall within the abiotic bucket.
Totally. Yep.
Great. So we've talked a bit now about how the technology works and sort of broad strokes, about measurement, wanting this carbon removal to be additional, measurable, permanent. What about the economics and also social science behind marine carbon dioxide removal? What kinds of questions should we be asking when it comes to the viability economically or the viability in terms of, say, community perceptions or public acceptance of this technology?
Yeah, I think both of those have very different considerations because from a cost perspective, that's why folks are so excited about ocean carbon removal, because its potential to deliver a ton of carbon dioxide removed and stored at much lower cost relative to a lot of other approaches. Listeners who have looked into carbon removal are probably most familiar with something called direct air capture. So you can kind of imagine fans on land that are interacting with the atmosphere, scrubbing CO2 out of the atmosphere. That takes a lot of land space. That takes a lot of energy to take CO2 from 400 parts per million and concentrate it up to 99% purity for storage. It takes a lot of then land and energy to move that CO2 to a proper geologic storage or utilization. And all that leads to really high costs. The ocean, again, is already capturing and storing about 1 billion tons of CO2 per year. The ocean already has its own favorable energetics for these types of chemical reactions, and there's lots of ocean space, so not as limited relative to land approaches. All of that means that, at least in theory and in some projections for scale, ocean carbon removal can deliver a ton of carbon dioxide removed and stored for much lower, and a lot of projections have well under $100 per ton. So that gets people really excited. But then you ask about the societal side, and I think that's what makes people nervous, because the oceans are already negatively impacted by climate change. And if there's one thing humans have proven time and time again to be really good at, it's driving something that has unintended negative consequences, despite our best intentions. And so in that mCDR community, there is a lot of attention paid to ensuring that these technologies are developed, deployed, and scaled in a way that is aware of and monitors any potential negative consequences and mitigates against those, so that communities interacting with the ocean, or just communities that care about ocean health, have their concerns adequately addressed, and that while we're striving to save the climate and have a habitable planet, that the ocean can also continue to be habitable for marine life. And so right now, a lot of that includes companies like Vycarb. We work very closely with independent research groups at universities, at nonprofits, some that are companies specifically now emerging, helping mCDR companies monitor and mitigate some of those environmental impacts. But on the other hand, what we've developed at Vycarb and what a lot of mCDR technology developers are focused on are actually ways that we can draw down that CO2 while having what are called co-benefits, so actual positive impacts on ocean health. So all that absorption of CO2 by the ocean that's happening naturally, because we put so much CO2 into the atmosphere, is essentially causing acidification. So that CO2 turns to carbonic acid because we're not adding, or there's not enough of those other ions in the ocean to convert it to bicarbonate fast enough. That CO2 stays as CO2, turns into carbonic acid. And that's really negatively impacting a lot of ocean ecosystems. A lot of my work as a climate scientist prior was focused on that problem of acidification, because it's that intersection of ocean health and ecosystems with carbon cycling and the climate. And so a lot of those carbon removal approaches I mentioned, particularly those that are focused on that abiotic pathway of either pulling CO2 out or adding things like calcium and magnesium to convert that CO2 to bicarbonate, they have an added benefit of reducing that acidification. So that's great. But again, making sure that those are deployed at scale in a way that doesn't have some other unintended consequence separate from acidification is really the focus.
I actually was just reading an article this morning about how ocean acidification is at an all-time high, which I thought was timely because I figured you were going to be talking about the co-benefits of reducing ocean acidification by some of these technologies. So,
yeah, and the more CO2 we put in the atmosphere, the less the ocean is able to buffer that CO2, and the worse that acidification gets. And one of the things in my background as a climate scientist, and actually in New York State, I was on the New York State Climate Impacts Assessment, which was a statewide effort to assess what are the different impacts of climate change in New York specifically. My focus, I with another author, Becky Schufer, we focused specifically on the part of that report that focused on ocean acidification in coastal New York. And so we talk about it in kind of global oceans, but really the global ocean is a amalgamation of different ocean systems. And some of those ocean systems are much more susceptible to acidification, where they're seeing not only is it getting worse in the global ocean, but getting really acute and pronounced in specific locations. That's having an impact on fisheries, ecosystems that I think we'll see more and more of if we don't act quickly.
Can you tell us a bit more about Vycarb's technology and how it works to remove carbon dioxide and store it in the ocean?
Yes. So, I mentioned that in that abiotic pathway, the idea of adding things like calcium and magnesium that allows that CO2 to convert to bicarbonate so it's permanently locked away. There are a lot of different ways folks have tried to get at this. And then I also mentioned that measurement and verification being the real bottleneck, particularly in the ocean, because CO2 and bicarbonate are these massive pools, really hard to monitor small changes in that. And so a lot of folks have focused on what we call open system approaches. So again, we're going to spread a bunch of magnesium and calcium out into the open ocean. That's going to drive this chemical reaction over large spatial scales, long time scales, really attractive from a cost perspective, because you take a ship out, you put a bunch of calcium and magnesium out, wipe your hands, say it's done. But how quickly or how effectively that works for actually removing and storing carbon dioxide is the big question. So at Vycarb, we developed really a two-pronged approach, technology approach to solve a lot of those problems and actually accelerate and control that chemical reaction. So we have a closed system approach where we take in water that has excess CO2. So think our system right now is in Brooklyn's East River that has very high CO2. Because of that, it's very acidic. And that CO2 is actually escaping into the atmosphere. Again, thinking about the different spatial systems within what we would call the ocean. So some of these places are emitting CO2 from respiration. We're able to take that water that has high CO2, convert it to bicarbonate by adding calcium and magnesium in this closed system. But the other half of our tech stack is a sensing technology that we developed. And again, with my background in ocean carbon and climate science, a lot of my focus was on just developing new analytical tools to trace these types of molecules. We developed a first of a kind real-time sensor so that we can actually quantify the amount of dissolved CO2, bicarbonate, and carbonate that are in those waters. So as water flows through our system, we're able to quantify how much CO2, bicarbonate, and carbonate is there, add just the right amount of calcium and magnesium just to neutralize that excess CO2, convert it to that permanently stored bicarbonate, and then measure on the back end exactly how much of that CO2 was converted to bicarbonate. So on one hand, it solves the measurement problem and the permanence problem because we can show, yep, here's exactly how many tons of CO2 were converted to that permanent bicarbonate. But it also addresses that unintended consequence and societal problem where we're able to control the process flow rates just to the right amount to neutralize that CO2, but not overwhelm the ocean system with calcium and magnesium where it could have negative impacts. And the final thing I'll say is in that testing that we've done, we've also recognized that, yes, we can take CO2 that's present in some of these waters, but we can also take CO2 from lots of other sources. So I mentioned direct air capture. A lot of the energy and cost is in how you store that, how you sequester it. And today, the only real permanent storage solution for captured CO2 is injecting it in the subsurface in geologic formations, which is pretty limited in space. Not many locations have that as an option. What we've demonstrated is we can also add additional CO2 into this system, convert it to bicarbonate just as I described. And so now we also have a low-cost, controlled, and permanent carbon storage solution for lots of other upstream ways that capture or remove CO2. We can do that safely and effectively. And so that's really, then all of a sudden opens up that ocean system, not just for the carbon removal, but just on the storage side as well, which is a huge bottleneck.
And this additional CO2 that you can store in the ocean through this process, is this coming from point sources? Is this atmospheric CO2?
That's what's nice about this. It can come from really anywhere. So we work with some direct air capture companies where we can take their CO2, but we also work with companies that are capturing it from the point source. What we found is a lot of these industrial facilities that are emitting CO2, They're not anywhere near adequate geologic storage, but they're typically on coastal systems because they're using bulk dry shipping for their imports, or excuse me, their inputs for their exports. They're using oftentimes water for cooling the process or for some of the process chemistry. And so we can use that coastline that they're already co-located with. They can capture the CO2, but then we can provide that permanent storage. Because it's captured CO2 regardless of where it comes from, and it goes into our measurement controlled system, we can still ensure that it's being done in a way that doesn't have any of the unintended consequences.
You mentioned that you have this pilot at the New York Brooklyn Navy Yard. Can you tell us a bit more about that pilot and what you've been learning from it?
Yes. So this is our third pilot to date. So we started kind of very small scale demonstration in different locations. We worked back in 2023 with the East Hampton Shellfish Hatchery, recognizing, again, if this has the potential to deacidify waters, and shellfish hatcheries in coastal New York are highly susceptible to that acidification. Can we integrate into some of those systems and show that this has those added co-benefits, but is also safe? So we started with a small demonstration there. And then we had our second scaled up pilot was at the Trust for Governors Island in the New York City harbor. They announced climate solutions innovation test bed a couple of years ago. And so we did some piloting out there. And then these were all very small scale. So we said, okay, now we're ready to really test this at a larger scale. And our office is based at the Brooklyn Navy Yard. And so we worked with the Navy Yards. They have a program called Yard Labs, which is meant to provide that Navy Yard as a living lab test facility for lots of different climate solutions, everything from EV charging stations to mCDR. And so we were able to get access to the waterfront there to do a much larger longer term test there. So we launched maybe less than a year ago, but showing this now at the tons per year, so much more commercially and climatologically relevant scale. And some of the things we've learned with this technology across some of those different pilot locations that I described, very different water chemistries. What's nice about the East River is it's a tidal estuary, so it's brackish. So some days things like salinity can change by 10 to 15 parts per thousand, pretty significant changes in water chemistry, which is great for testing and optimizing this type of technology across different settings. I also mentioned that we add things like calcium and magnesium to drive that chemical reaction. So this longer term test pilot in Brooklyn has allowed us to test a bunch of those different types of calcium and magnesium. Because as we think about scaling, as we think about impacts, there will be different sources of calcium and magnesium present in different locations. Being able to test those in a small controlled setting like where we are now really allows us to assess which are suitable for this technology, which aren't, which provide the best cost and performance as we think about scaling. And then finally, CO2. So we started with that initial use case that I described, taking that already high CO2 water, converting that CO2 to bicarbonate, preventing its release. As we recognize the opportunity to take additional CO2, we've started testing now CO2 gas, where we're essentially just simulating what different concentrations of CO2 might be in the water. That shows its application or use in all of those different upstream carbon storage applications.
So what is your vision for deployment at scale of Vycarb's technology? And what questions, if any, still need to be answered in order to scale this technology and bring it to different contexts?
One of the things we're most excited about is that we really do believe this technology has the potential to be the largest carbon management solution in the world. We have the unique technology that allows us to fully control and accelerate that abiotic carbon storage pathway, fully measure it. And we really think that's what's needed to unlock the massive carbon removal and storage potential of the ocean, and do that anywhere that the ocean touches land or anywhere really that water and humans intersect. To get to there, again, a lot of the testing that we've been doing at the Brooklyn Navy Yard is looking at some of the different inputs that might be present as we scale geographically. Water conditions, CO2 inputs, mineral types. And a lot of our commercial work has been with different industrial sectors, different landowners, really globally. 2 weeks ago, I was in Norway, They've got a massive carbon capture and storage ecosystem there because of the oil and gas industry, because of some existing geologic storage work that's going on there, and lots of coastline, lots of industrial facilities that are on coastline. So working with some major energy or materials companies out there for different opportunities to deploy this technology. I then went to places in Asia Pacific, in Singapore, where in Singapore there's a carbon tax. There's about 60 million tons of CO2 emitted every year. And again, no geologic storage potential, but lots of coastline. And so how can we deploy Vycarb's technology there to provide a solution? So that gives a sense of truly global interest and scale potential. So as we test and demonstrate in Brooklyn, it's all about what are the costs, what are the performance metrics, what are some of the kind of water discharge requirements and implications that need to be addressed as we scale this up. And one of the things that is unique, I think, about our scaling approach relative to other carbon removal technologies and companies is we really do take a stepwise or an iterative increase in scale approach. So we're not saying we've done this at the tons per year, we're happy with it, let's go do 1 million tons per year. Largely because of that ecosystem impact question, we're really looking at where can we do this at 1,000 tons per year first, and then scale up to maybe 10,000 tons, but iteratively scale up and really understand how does this perform as we're moving lots more water and lots more CO2. And as we do that, how can we really demonstrate at each of those scales that, yes, there are no negative impacts, or even better, there are positive impacts that we can measure, and use that to build more, again, community support, community trust to scale this up as a climate solution.
Great. So let's talk a bit more about the legal and the regulatory side of this work. So I'll turn to Meg. Can you say a bit about what the current legal and regulatory framework is for marine carbon removal projects?
Yeah, and just at the outset, Garrett has made a lot of references to international projects and opportunities, but I'm going to focus on the U.S. legal framework, and maybe we can cover the international legal framework it's a whole different podcast episode, but lots to talk about in the U.S. So right now, there's no single U.S. law that says here's how to regulate ocean-based carbon removal. These projects fit within a patchwork of existing environmental laws, and which rules and laws apply really depends on where the project is located, what the activity is, and how the activity is being carried out. So the location matters because activities conducted within 200 nautical miles from the shore are within the U.S.'s exclusive economic zone, or what's called the EEZ. And these are governed by U.S. laws and regulations. So if you are planning to deploy within 200 nautical miles from the shore, you're not going to be looking at international law in the first instance. And then state waters and state jurisdiction over those waters generally extend 3 nautical miles from shore. So if your project is going to be within 3 miles of shore, then you also have to look to the state's laws to see what laws are relevant for your activities. The activity matters because discharging material, burying biomass, adding alkalinity, installing structures in the water column, they each trigger different statutes because, as I mentioned, we don't have one statute that looks to marine carbon removal. So you're looking at different regulatory regimes to see what might fit. And also the method, like how you actually execute the project, can matter for determining the permitting pathway. So at the federal level, projects that are within what we call the waters of the United States fall under the purview generally of the Clean Water Act. And the Clean Water Act has 2 main permitting programs that can apply to marine carbon removal. So Section 402 of the Clean Water Act covers discharges of pollutants from a point source into U.S. waters. And pollutants are defined really broadly. So rock, sand, biological material, and also heat are all considered pollutants under the Clean Water Act. So if you're adding alkalinity or other minerals to the water, as Vycarb's technology does, or if you're doing something to heat up the water, then this could trigger a permit under Section 402 of the Clean Water Act. And in most states, it's actually the state that administers this program on behalf of the EPA. There's another Clean Water Act section that applies probably to more of the biotic projects that Garrett was talking about earlier. This applies if you're placing fill material into the waters of the United States, and that is defined as material including rock, sand, even wood chips. Anything that has the effect of either replacing a portion of the water with dry land or changing the bottom elevation of any portion of a water of the United States. And this permitting is handled by the U.S. Army Corps of Engineers.
Great. And what section of the Clean Water Act is that permitted under?
So that's Section 404. Now, Section 404 is most commonly used for mCDR activities if you are placing fill material in waters of the United States that are landward of the baseline of the territorial seas. So, for example, a biotic project that is going to take place in a bay or a harbor. If you're depositing material in ocean waters, again, depending on the specifics of the project, the Marine Protection, Research, and Sanctuaries Act, which is more commonly known as the Ocean Dumping Act, likely applies. The Ocean Dumping Act regulates the quote-unquote dumping of all types of materials into ocean water that are within 12 nautical miles of the U.S. coast. And dumping is broadly defined. It's any disposition of material of any kind. Permits under the Ocean Dumping Act are issued by the EPA, and the permit will actually specify what type of material is permitted and the location of the disposal site. Discharges from point sources into waters of the United States. So, for example, mCDR activities that result in the discharge of effluent through a structure into ocean waters are regulated not under the Ocean Dumping Act. They're regulated under Section 402 of the Clean Water Act, which we talked about a little bit earlier. But if you're in ocean waters, not inland waters, you're 12 nautical miles from the U.S. coast and you're depositing materials into ocean waters not via a point source, then an EPA permit under the Ocean Dumping Act is very likely required. An EPA website actually has some good guidance about the differences between the Clean Water Act 402 program and the program under the Ocean Dumping Act and which permitting program should govern. I believe that EPA actually issued its first permit for a marine carbon dioxide removal project under the Ocean Dumping Act in April of this year. They issued a research permit to the Woods Hole Oceanographic Institute for an ocean alkalinity enhancement project off the coast of Cape Cod. There are also a couple of other federal statutes that might come into play, again, depending on the specifics of the project. The Rivers and Harbor Act requires a permit for any structure or work in navigable waters. And the issuance of federal permits also usually triggers environmental review under the National Environmental Policy Act. And there are also consultations required under the Endangered Species Act and the Magnuson-Stevens Act for essential fish habitat. You will also likely need state coastal zone consistency reviews because these projects often happen in coastal waters. So that is a very quick overview of the federal permitting regime. In addition to the layer of state laws that might be applicable, there are a lot of different federal laws that might come into play, again, depending on the specific circumstances of your project.
So it's a very multi-layered permitting process on the federal side. And now what if one of these projects is located within state jurisdiction?
In New York, the State Department of Environmental Conservation administers permitting under Section 402 of the Clean Water Act. It also regulates tidal wetlands and in-water work. So if your project is in mapped tidal wetlands, you may also need a tidal wetlands permit, though there is a research exemption that can apply to small pilots. And if you need a state permit from the Department of Environmental Conservation, that usually triggers an environmental review requirement under the State Environmental Quality Review Act, or SPRingBoard. If you are putting structures on or, say, burying biomass in state-owned lands underwater, you may also need an easement or a license from the State Office of General Services. And there are also local requirements. So in New York City, we have to consider, for example, the Waterfront Revitalization Program, which checks for consistency with the city's coastal policies. And other cities and localities have their own jurisdictional requirements and regulatory requirements as well. So again, like at the federal level, it is a sort of patchwork of things that might apply depending on the very specific details about where the project is located, what the project is, and what means and methods are being used.
Now, have any of these projects actually been permitted yet?
Yeah, so there is an organization called Ocean's Vision that tracks mCDR projects, and they've identified, as of the last time I checked this morning, 46 projects that are either in operation or have concluded globally, many of which have received the necessary permits. Some of them are located in other countries. But I do know that there is a company called Carbon, which does electrochemical ocean alkalinity enhancement. They have a 2-year pilot project in Washington State, and they actually received a Clean Water Act Section 402 permit, which is the permitting process for discharge of quote unquote pollutants that I was just describing. Another company, Vesta, has received a permit from the U.S. Army Corps of Engineers and also from the North Carolina Department of Environmental Quality to add carbon removing sand offshore in North Carolina. And then there are also pilot projects. I mean, I think most of these are still considered pilot projects because they're all pretty small scale. Like, we have not seen large scale deployment of this technology yet. But there are also many pilot projects that have engaged with regulators without going through the full permitting process. So how I met Garrett is that our firm worked with Vycarb on their East River pilot at Brooklyn Navy Yard. And we identified that for this specific technology, a Clean Water Act Section 402 permit might be required because the model involved adding alkalizing minerals into Vycarb's system and then releasing amended waters into the water column. I know there have been some changes to the business model, but that was sort of the original proposal. And what we did is we had a pre-application meeting with the New York's DEC, and DEC actually gave us the feedback that they didn't think that a speedies permit or a tidal wetlands permit would be required because this was a small scale project. We had framed it as such. We were specifically going into the meeting saying, this is for research. We're doing it for less than 1 year. We need to gather information. So in that case, we applied for what's called an out of jurisdictional determination, and we didn't actually have to obtain the full permitting. We didn't have to go down the full permitting process, but we did have engagement with the regulators. But for a larger or longer term deployment of the same technology, we would expect to have to go through that full permitting path and do the associated environmental reviews.
It may also be a question for Garrett. I'm curious if you can speak to any specific feedback that you've received from state or even local regulators in implementing the pilot.
I mean, one of the things that's just so, to Meg's point, like there's no existing framework for mCDR specifically. And I think in the initial conversations we had, it was just like, what the heck are we proposing to do? Like, what is this? And also Meg mentioned what's under consideration is the purpose of the project. And so I think for us, the purpose being ultimately, a pollution remediation project, if you think of CO2 as a pollution, or if you think of acidification in the East River as a pollution. I think those were the discussions we had is what's the goal? What are we trying to do here? Because it was focused on the research and testing, what are some of the things that we'll be testing and what's the scale of impact that we'll have through that testing? Those were some of the discussions we had. And because all of this is first of a kind, it's not like this is an existing technology that we've got 12 months of performance data on to show a regulator, here's exactly what the impacts are. And so a lot of it was, well, here's the data we have from the smaller scale trials we've done, and here's a literature review of similar types of approaches. In the aquaculture space, there's something called seawater buffering that's done, where a lot of shellfish hatcheries or other aquaculture applications will do similar chemistry of what we're doing, adding calcium and magnesium to reduce the acidification. And so using some of the literature there to show what some of the impacts might be or lack of the impacts that we expect to substantiate or support their review of this first of a kind technology for, again, what is meant to be a positive climate and environmentally positive project, but we recognize we're reviewing this from what are the potential risks, what are the potential negative impacts.
Yeah, I mean, just to add to that, actually two separate thoughts. So the first is, Garrett, you just mentioned this, but when we first approached the DEC about this project, we had discussed making the argument to the DEC that we don't need to get a Section 402 permit because the express purpose of this project was to remove a pollutant, that pollutant being carbon dioxide. And we didn't know how DEC was going to respond to this argument, but I think there is there is a viable argument to be made that you're not adding a pollutant with this specific technology, you are removing the pollutant. And in fact, the way that Vycarb's system worked, you aren't actually even adding the minerals into the open water. It's being added to a system, and then what's being released is amended waters. So that was one argument that we actually didn't even get to, because the DEC was like, yeah, we don't think you really need a permit for this, especially based on the research bent, that the goal here of being a research project. The second thing I'll say is that the regulators, first, again, to echo Garrett, they were very concerned with impacts on marine life and impacts on the ecosystem. That's really their purview, is to make sure that there are no activities that come in and disturb the ecosystem. Second, I think they were really impressed by Vycarb's monitoring technology and the way that there was going to be constant data generated and constant monitoring. So that, I think that in future projects for future companies looking to get permitted, thinking about how you're going to ensure careful monitoring. Maybe it doesn't have to be the exact same like real-time monitor. I think with Vycarb, the monitoring is 24/7. I don't know that that is necessarily required, but I think that that is something that gave DEC a lot of comfort in this situation.
And thinking about the fact that, as you said, we do sort of have to retrofit these environmental laws and regulations that are designed for preventing pollution for technology that is about amending waters. Do the existing regulatory frameworks we have provide a clear and workable path for marine carbon dioxide removal, or are there gaps in these laws and regulations that make deployment difficult?
There are definitely gaps. It is certainly feasible to work within the existing statutory framework, especially at the research and pilot scale, but the statutes just weren't designed with carbon removal in mind. And so the process can be slow, fragmented, and obviously there's a lot of uncertainty. And this is a broader problem in the climate change community. I think trying to utilize these existing environmental statutes that were passed in the 1970s to respond to pollution, to address climate change. It's a big issue. And like in other contexts, the tools exist, but they're not purpose-built for the scale and for the specific issue and for the speed that I think is really needed to deploy quickly.
If I can jump in, one question I have, maybe that gets to that. Meg, do you think that some of the work that Vycarb is doing now, you mentioned some of the other companies doing first-of-a-kind permitting for their ocean carbon removal projects, do you think these early permitting or regulatory permission structures provide precedents in other U.S. Jurisdictions for scale up? Or do you think, if we want to go to a state where this has not been done yet, are we starting from ground zero, or do some of the existing permits and projects actually support and help fill some of those gaps?
That's a great question. Every state is going to operate independently and is going to make their own decisions. So one state might say, yeah, this is a research project. And the other one might say, no, we really need you to go through the Section 402 permitting process, because this is absolutely a pollutant being added to waters of the United States, because heat or alkalizing minerals are a pollutant if you look at the regulatory and statutory definitions. However, that being said, I think pointing to successful projects that have been undertaken in the past, even in other states and other jurisdictions, and importantly, pointing to successful data and successful monitoring and showing that these other projects haven't created a negative impact is something that I think regulators are going to want to hear and they're going to want to know about, and that might influence their decision as to what permitting regime might be required. So I would say, in the legal world, we say persuasive authority, but not binding. I think that it is persuasive if you are going to another state and you say, hey, we've done this successfully in New York. New York didn't require a permit. New York implements the Clean Water Act. And, they said because this was a research project, we could do our project in, less than 1 year. We wouldn't need a jurisdictional permit. We have all this data, which shows what a positive impact we made on the ecosystem and how there weren't negative impacts to marine life. I think that that's persuasive, but again, it's not precedent setting in a way that would enable necessarily a easier time in another state.
Great. So we've talked about the science, we talked about the technology, we talked about law and regulations. In the bit of time we have left, I want to talk a bit about community engagement. So when you're thinking about planning for and citing an mCDR project, which communities and groups are important to engage and at what point in the process? And what are some of the best practices that you've learned for engaging with communities and with regulators?
Yeah. It's interesting because I do think of a differentiated approach between the local communities and the global community. And we're just in 2025, even local projects are subject to global scrutiny because there are so many eyes on climate solutions and marine carbon dioxide removal. I think both of those are certainly supported by a lot of the work that I mentioned we do with independent research groups. So we work with different universities. We've got the University of Rhode Island's Ocean Carbon Lab doing independent validation of our new sensing technology. Again, this is a new sensing technology, and so showing that an independent group that has their own expertise in assessing ocean carbon measurement or monitoring approaches, them validating our measurement is supportive of showing that what we are measuring to control and ensure the safety of this approach is valid. But then we have some other groups. There's a group that was a spin out of MIT called AtDepth. And they've deployed a suite of sensors around our system, measuring what's the flux of CO2 out of the waters near our system to show that it's permanent, measuring things like chlorophyll and dissolved oxygen to show a lack of negative ecosystem impacts in those waters. And then having those data as they're generated public, I think is really helpful. Meg mentioned groups like Ocean Vision. So we're part of the Ocean Vision's Launchpad program, where we have now a number of advisors who were formerly at the Department of Energy, who are at Scripps Institute of Oceanography, who are at MBARI, all kind of experts in ocean carbon solutions, all providing their own independent assessment or support to make sure that we're scaling this in a scientifically responsible way. And then just again, as we work with buyers in the voluntary carbon market, which is a global economy, having that data that we're generating made public and shared with those buyers is really critical to think about scaling and getting global support. But then in the local ecosystem, we're actually talking on the Monday after 2025 Climate Week. And I launched the company and Climate Week of 2022. Each year in Climate Week, we've used that local hub of climate discussions as a chance to showcase and share the work that we're doing, so we do open houses where we allow anyone to come and see what we're doing, ask questions. I do think folks seeing the system in the water in the East River just makes a lot of these concerns. It makes it easier to address those concerns. To Meg's point, you can read about, okay, we're adding magnesium and calcium to water. That's classified as a pollutant. We're really concerned about that. But then you see the system, it's like, oh, what comes out of our system is just water. Right. And that magnesium has been fully dissolved. It's neutralizing the CO2. You can see the data coming off of it right away that, yep, there's less CO2 in those waters, but the pH is still safe. It's actually healthier than the pH of the water that came in because of the acidification there. That's been really helpful. In New York City, we've worked with a number of other groups. So there are some nonprofits that focus on local water quality, and we've presented at their annual conferences, sharing what we do and again, answering questions and really getting excitement about what scaling this kind of solution up looks like. And then finally, we also think about kind of the best way to address some of these questions is to highlight the opportunities that come out of this. And certainly for local communities that can deploy this technology, a lot of those opportunities are workforce development. And so there's the New York City Harbor School, which is an awesome, school for middle and high school students who are specifically focused on training in kind of coastal and maritime sectors. We've hosted a number of their students. Well, actually, we've hosted a number of their classes to come out and do research projects and learn about our system, but also hosted individual students for internships. This past summer, we had a student from the Bronx Science School, and this is actually his second summer interning with us. And so I think that's also helpful to show we're not just taking advantage of the New York City location to scale this up, but really trying to build roots, deepen roots, and stimulate overall workforce and economic development to highlight this isn't something scary that could have negative impacts. This is a real opportunity that as we scale it safely can benefit lots of different people in that community.
And before we wrap up, so Meg, you and Garrett have worked together on permitting the pilot project in the Brooklyn Navy Yard. What are some best practices for an attorney and climate tech startup partnership in the future?
So Vycarb came to us when they had a pilot location in mind. And from there, we did two things in parallel. We first mapped the permitting path based on what the activity was. And then we set a pre-application meeting with the New York DEC, as I mentioned. And it was after that discussion that DEC invited us to pursue this non-jurisdictional determination, which was, a written finding that the project didn't require a speedies or tidal wetlands permits. But for subsequent iterations, both with when Vycarb was looking at other pilot opportunities after Brooklyn Navy Yard and also with other clients, we've started at the site screening, which I think can be very valuable because it can help companies identify sites that have the clearest path for a project at a research scale. So in New York, for example, there are a lot of submerged lands that are publicly owned by the city or state. And if the project entails obtaining proprietary permissions for installation in the seabed or amendments to the seabed, again, thinking of more of the projects that are biomass burial, etc., that permission can be extremely time consuming. And so it might not be appropriate for a research scale pilot. If speed is critical and if you want to have some pilots up and running, we can flag that early and help teams prioritize locations where obtaining such permissions is a little more streamlined, such as if a private landowner owns those lands underwater. But I think getting involved with looking at various piloting locations can be helpful given the regulatory patchwork that we're working with and how different laws and regulations apply based on, again, the exact location and the exact nature of the project. And we've also been involved with helping pilots think about how they want to frame their project to help streamline permitting and help sell the story to the regulators. I don't know, Garrett, do you have anything to add?
Yeah, I'll just add, because we get this question about permitting all the time, whether it be from customers, investors, potential partners. This is a new thing. All of the discussion we've had today helps answer a lot of that. But my best answer to how is a startup going to address this complex, costly, time-consuming permitting question to ensure success, and I say, well, we engage with really good regulatory counsel like Meg at SPR to guide us in that we're not doing that alone, and we shouldn't do that alone. And so to Meg's point, I think we engaged early. Frankly, I wish we had engaged earlier. And as I know other startups in the mCDR space that are emerging, and they ask me, how did Vycarb get our system in New York off the ground? I funneled them straight to Meg and said, yeah, you just got to talk to the right people who know how to, not only what the process is and how to navigate that, but exactly as Meg said, how to message that, how to strategically approach it based on what the startup needs, what the scale of the project requires for where we are and as we move forward.
We do our best to help, and it is a really a fun and interesting challenge to figure out how to best move forward given the current regulatory regime.
Well, thank you so much, Garrett and Meg, for joining us today. This is important work, and we're appreciative of this conversation on both the state of the technology in mCDR and also of the regulatory field in implementing these projects. And to our listeners, thank you for joining us at SPRingBoard. Stay tuned for future episodes where we'll continue exploring the intersections of law, policy, and the environment.
The content of this podcast and its supplemental material is for informational purposes only and should not be considered legal advice. The views and opinions expressed in this program are those of the speakers in their individual capacities and do not necessarily reflect the views or opinions of Side Padgett and Rizal and/or any of the clients they represent.